So we've talked about a number of symmetries, but we were applying them all to an infinite cylinder. What's helpful if we think about three shapes that have some basic overall symmetries. And in general, we're going to be analyzing the fields and charge distributions that match one of these general shape categories. Trying to do electrostatics, so thinking about the electric field from really complicated charge distributions, for instance, say the shape of an apple, that pretty much requires a computer to do it. It's very, very difficult to calculate that. So if I wanted to actually understand the field from an apple, I would use a few different qualitative techniques, and overall the best approach you could say is, well, an apple is similar to a sphere. So that's one thing to keep in mind here. We really have to limit ourselves at the introductory level to these shapes. So I'll go through them individually, but we want to think about the symmetry of the charge distribution, the symmetry of the electric field it creates, and then what we might start applying this to. Because again, spheres, cylinders, and planes we met in the previous chapter. But we can start thinking about more complicated shapes now, such as multiple nested cylinders or multiple nested spheres. So let's focus in on just a plane to begin with. So the plane means, and this isn't a true side view, this is a 3D view. So from the side view, it would look like that. We would have our charges, of course, on the surface, and then we would know that we have this electric field pointing outwards, which I'm attempting to draw uniformly, but it's really hard to do on this screen. And the key is, if we're doing vectors in particular, that it doesn't actually get weaker as you get further away. Now, that idea, the fact that it doesn't get weaker as you get further away from an infinite plane, that's actually something that you wouldn't get from the symmetry alone. However, the notion that it has to be perpendicular, oh, that's definitely not symmetric. That's terrible. I'm so sorry. Let's erase that. The idea being that we also have a reflection plane here. So whatever we have on the top needs to reflect down, so that's good. And we have a translational symmetry because this is an infinite plane. So whatever one you have here needs to repeat over. Now again, notice that this is three-dimensional, so this is one side view, but we would have another side view that really looks just the same as this. So one example of this that you have already met is the infinite parallel plate capacitor, where we just think about this as the sum of two planes. Now, when we think about the finite parallel plate capacitor, where we actually put edges on, we lose the translational symmetry, right? So just like in the cylinder example, now this point and this point do not look the same, but we still have this reflection symmetry, and we still have a sideways reflection symmetry over the center. So if I had a finite parallel plate capacitor and I wanted to draw what the fields were, I could use this to think through how it changes, because I'm actually losing my translational symmetry, but the rest of them need to be the same. So again, this can be a technique for qualitatively thinking about more complicated shapes. So then we have our cylinder, the one we've already talked about a lot. And one thing that we'll run into is the idea of coaxial cylinders. And what this word means is that the axis is the same. So the center point of one cylinder, the tiny one on the inside, is the same point as the center of the cylinder on the outside. And this now, we have two cylinders. Now maybe we're putting a charge on the outside, maybe we have a charge on the inside, and we start to ask, what is our electric field doing? Well, it still needs to have this symmetry because every aspect of our charge distribution now has that symmetry. So coaxial cables are really interesting because they're objects that actually come up. So certain types of cables that exist are coaxial cables. They're typically cables you find in scientific environments, maybe not necessarily in your house, but this is a case something we can think about explicitly. So the cylindrical symmetry for nested cylinders is something that can come up in some real-world problems. Spherical symmetry, everything has to point away from a center point. And again, where that gets more complicated is concentric spheres. So it might be a little hard to see what's happening in the picture, but we have an outer sphere that is hollow, and then we have an inner sphere. Maybe it's hollow, maybe it's not, but they actually share a center point. So we have two different radii cylinders sharing a center point, and then maybe we put charges on the center one and ask what's happening. Now, because our charge distribution, and maybe we have additional charges on the outer one, because our charge distribution has spherical symmetry, our field must have a spherical symmetry. So that's again the idea here. So the spherical symmetry of the original, just a plain sphere, isn't very exciting. The other thing we can do that is really hard to draw, but imagine you have a sphere that on the inside has a changing density. So at the center, it's only a little dense, and then it gets more dense, which, I can't draw very well. And then by time you're to a certain radius, it's even more dense. So basically, we have density as a function of radius. So in this case, you still have a cylindrical symmetry. For a given radius, it's the same everywhere at that radius, but now it's a much more complicated system than if you just have a solid sphere or a spherical shell. So be ready for something like this, where density is varying with radius, but we've preserved our spherical symmetry. So you can actually still figure out a lot about what the field is doing. So again, these types of symmetries are going to come up. Some people have a pretty good sense for symmetry. Maybe you've done artistic work before, engineering work, something where you think about symmetries. For other people who maybe don't have as much practice with visual reasoning, this can be a little more challenging, but it's something that you'll need to practice a lot for this chapter, and that will come back up later in other topics in this class as well.